Hello, everyone. Welcome to ABMA's Inside the Boiler Room. I'm Scott Lynch, President and CEO of ABMA, and your host for today's podcast. I'm excited to be joined today by Tristen Gitzel, Engineering and Drafting Manager from ABMA member Northern Blower. We're going to discuss the importance of the fan as a major component of the boiler room. But before we jump into today's topic, I want to recognize our new followers on YouTube, as well as those that continue to listen on most podcast platforms. Please like our content, please continue to subscribe, and please let us know if you have any other ideas and thoughts for future episodes. All right, so without further ado, it's now time to bring in our guest. So here we go. Look at this, it's like magic. Tristen.
I'm here.
Welcome to Inside the Boiler Room.
Thank you. Thank you so much for having me. I'm very excited to talk fans.
And so we could probably talk about how fans work in very cold temperatures because you're actually in Winnipeg. Is that right?
That's right. Yeah, and it's in Winnipeg, Canada, and Manitoba, just kind of for north of North Dakota. It's the place we drive to go shopping is Minneapolis, just like everybody else.
Wow. Okay. All right. There you go. But you have a hockey team, though, so you have something.
And they are on a tear. Yeah, they I think I forget what it's at now. 15. They were at the leaderboard for most wins in a season.
Wow.
So I don't know if
all right,
make it, but we'll see.
All right. Well, I think it's been a long time since a Canadian team won the Stanley Cup, so maybe this will be the year, right?
We could use one.
All right. Well, so we always start out by trying to give a little context to what we talk about by learning a little bit more about the podcast guest as well as the company. So let's start out with just discussing your background and how you kind of worked your way to the boiler industry.
Yeah, right on. My name's Tristen Gitzel. I am a professional engineer in Canada. And just so for the audience's benefit, in Canada, it's a lot like in the US, the PE designation. It's a protected term. Engineer is a protected term in Canada. So what that means is to practice engineering, you need to be licensed by our provincial regulator. And so what that means for me is I have an undergraduate degree in mechanical engineering. I work under some other professional engineers for several years, and then there's a kind of professional and ethical standards that I have to meet, saying things in the public interest.
All right. And so how did you get to Northern Blower?
Yeah. So, I've been in manufacturing and kind of engineering for most of my career, but lots of different industries from started in aerospace and then agriculture, machinery, HVAC is kind of where I started and I'm kind of back to. Great opportunity for Northern Blower, and I hopped on board as the engineering and drafting manager, leading the kind of the engineering and manufacturing team, I guess, as obvious as the title is. And so what we do is we solve customer problems, and we use fans as our medium to do that. And
that sounds like a good. So and give some before we jump into like discussing like the basics of fans, sizing of fans. How big can some of these fans get?
Oh yeah, really, really big. And I don't know if you can tell from the pictures behind me, but they barely fit on the truck sometimes.
Yeah.
Or even bigger, where we have to ship them in pieces, just to give you an idea. So there's kind of everyone thinks of a fan like a ceiling fan, but
right.
What we're talking about are these huge industrial machines that are quite engineered and in depth, and lots going on behind them.
So then let's jump into that and just talk about at a basic level, why is a fan so important to the boiler system?
Well, I mean, yeah, all the combustion air, right, is the name of the game. So you want to have, not only do you want to have the air there, but you need to have the right amount of air and not, too rich or too lean on your combustion. So, you want to have something that's dependable. And, if you think of something like a hospital power plant or any power plant, it's got to be, very dependable, very able to be dialed in just right. And some of these things are, these really large wheels of fans, maybe 10 feet in diameter, right? Spinning, sometimes, thousands of RPM,
Right.
revolutions per minute. There's a lot of engineering that goes to make sure that that's going to last for 20 years.
So, okay. So we kind of talk about like, what the, you have the fan and why it's important and how it helps with airflow and other things. But really in today's environment, energy efficiency is king. Energy, making sure that you're being as efficient as you can with the energy source because of costs, also because of environmental impact, right?
Mm-hmm.
So talk to me about the different factors of fan efficiency. And my son keeps calling me, which is what it is, even though it's on Do Not Disturb.
Yeah.
There are certain people that can leak through, and he happens to be one of them.
Mm-hmm.
So we're talking about fan efficiency here. So we're talking about the diameter, the speed, the design of the blades at different pressures. Talk to me about that and kind of how all that comes into the to the formula and how all that impacts the end user and the boiler system.
Yeah. So I'll just start by just taking a big step back and just say, what does efficiency in a fan mean, right? And so, engineers would say, efficiency is like the useful work over the input. But, the useful work of a fan is moving air. And then all the other stuff that you get, the noise, the friction, and the heat is all the waste, right? So then, the efficiency of the fan is the useful work over the power that you're going to put into it. And so in general terms there, the what matters on power to move air is kind of three things. The airflow, so how much volume of air do you need to move, the CFM? How much pressure differential? You're blowing it through a really big tube or a really small tube, and you can imagine that you need more energy to put it through a constriction. And then the density of the air itself, right? Lots of different things have different, like in Canada, it gets to minus 40s, right? So if you're blowing cold air, it's a lot denser than if you're in a power plant exhaust system where it can be up to 600 Fahrenheit or something. So the density of the air actually changes quite a bit, and that matters as well.
Okay. That makes sense.
Okay, so then...
Well, I know, keep going. You keep going.
Yeah, I'll keep going, yeah. So then you have a whole bunch of different fan types and blades and shapes that can move that air, right? So you can have a really big diameter wheel, you can have a small one, they could be running at different speeds. There's different blade types now. So think about an airplane and like that teardrop airfoil, like that's kind of the best way for is efficiently moved air, which is why airplanes have that shape. But there's lots of other ways to do that. And then to get it more complicated, that fans are really different in such, that they have different, they match a load, for example. So what I mean by that is they'll all have a fan curve, which is kind of just a plot of a graph where you're plotting the airflow and pressure. And so depending on the pressure and the system that it's in, it kind of also tells you the efficiency and the amount of air it actually moves. So now I've gone to efficiency. And so like all fans are kind of tested in this best case scenario. Oh, I lost Scott for a second. And so, think of your refrigerator, for example, or your washing machine at home. Everyone gets that tag that's got an efficiency rating on it. And it doesn't change depending on the food that you have inside your fridge or the clothes that you have inside your washing machine. But fans are quite a bit different, where depending on where you select it, the efficiency changes a great deal. And so, yeah, that's kind of the introduction to efficiency on a fan.
Yeah, and what's interesting about that is that it seems like it's one of those things where people don't understand that there is different efficiencies in the fans, why they would need a certain efficiency, what it's really going to add to them. They know they need a fan in a boiler system, or a boiler system includes a fan. And especially on an end user side, if the fan isn't working properly, I'm not sure they would even know that, right? I mean, like, unless it breaks down or it's making a lot of noise or something, you know, so it's kind of like a silent piece of the boiler. And it's like and maybe silent, well, silent, hopefully, I guess, in some way.
Yeah.
Right. But it's kind of, it's something inside the boiler that is not really understood by the end user. Do you agree with that?
Yeah, I think so. It's a lot like I think a lot of infrastructure, right? Or like your car engine, where it's there and it's working, but if it doesn't work, then that's a problem.
Yeah,
right?
well, and I think that talks to a lot
kind
of
of magic inside. Yeah.
Yeah, but I think it's a lot of the stuff in the boiler room, especially from a in certain situations, like if the boiler is running and operating, then it's got to be fine. People don't really understand the nuances. And I guess the other reason why I wanted to kind of talk about the efficiency end of it and why there's a passion around this is I think that when an end user is looking to increase the efficiency of their systems, they need to understand that there's many components within the boiler room that can help that efficiency.
Yeah.
And including the fans, the burner, whatever, the control system, all of those play into one big answer. And it's not just one or the other. It could be many parts.
Yeah, absolutely. Yeah.
So you shared a term with me, FEI, and so I'd like to know, like, can you talk about what that is and why it was created?
Yeah. So I guess I kind of mentioned this before, and I'll hit on it again, that the fan efficiency it changes a great deal depending on where you select it. So just imagine there's a fan that's too big or there's a fan that's too small. You never really are picking right on the right spot that you want it to be. There's ways to design a custom fan to do that, but
right.
Most senses there's a Goldilocks zone.
Yeah.
And so if you can think of like we make industrial fans and blowers, but not maybe everyone can envision what that looks like in their mind's eyes. So just think of a ceiling fan or like a household fan. If you want more air, you could make the fan you got go like spin it really fast. You could find a way to speed it up, exceptionally fast. It's going to blow more air, but it's going to be a lot noisier, right? It's going to make a lot more noise. It's going to make a lot more heat when it's running fast and spinning. And so what you could do if you wanted to move more air in your house, you could just go out and buy a bigger fan that's running slower and it's going to be quieter. But this is kind of the point, right? So the bigger one costs more.
Right.
And the efficiency is better. So like, how do you know which one to do? Like, how could you do a cost benefit analysis of that?
Exactly.
So that's where AMCA came in. The Air Movement and Control Association developed this FEI called the Fan Energy Index. They had some other terms before that, but FEG is kind of the predecessor. But it wasn't quite clear enough. So what they said was, okay, so for any given duty point of fan, so your static pressure, your CFM, cubic feet per minute, and your density of the air, multiply these together, and you can calculate what the power draw of this fan is. And they said, well, we'll just use a reasonably efficient fan. How much power would that be?
Right.
And then they said, okay, now pick at the fan you're about to pick. What power are you expecting it to draw? And that's very easy to calculate. So then you would say, compared to this reference fan, am I using more energy or less energy? And so if you're using less energy than their reference fan, your FEI is going to be greater than 1.
Sure.
And if you're using more power, it's going to be less than 1. So that was kind of the aha moment for everybody, I think, and
it was a way to easily explain how you're getting to the numbers you're getting to, and it actually probably helps the manufacturer to share their information because it's much easier to understand, and it's like not just some formulas in the backdrop.
Yeah,
It's
exactly.
telling you the difference between the two.
Yeah, because like if I told you, oh, our fan is 68% efficient instead of 60, like you're gonna laugh at me, right?
Right. Yeah. Right. Yeah. 100%.
So
Yeah.
So I think it's a really smart way that they did this.
And so is this so where is this available? How is it kind of used from like on the consumer side, or how is it used when you talk about your products?
Mm-hmm. So yeah, like I guess I think most manufacturers are putting it on their proposals now to customers, the FEI, and then the nameplate I think also is showing that when you get it delivered to you.
Okay. So it's also a way to compare apples to apples as well as different types, and you can talk about all of your products in terms of that, so that maybe helps people understand that a little bit more.
Right. And like, there's different, like I mentioned, different blade types of different fans, right? So now do you use an efficient blade type running faster, or do you use a bigger fan that's less efficient? But so there's lots of ways now to compare what the kind of the best case scenario.
Yeah, that makes sense. So we wanted to do the last couple of questions and really kind of have somebody understand the uniquenesses. So you've brought a chart that we're going to pull up in a second that is going to help kind of do a comparison, and we're going to talk through that. Obviously, people that are listening to the podcast will not see the chart, so we're gonna tell those listeners to go on YouTube and look. But we're going to try to explain what we're also talking about here. And that's going to help kind of talk about the investment payback and all of like that. So I'm going to pull that up right now. Okay. Yeah. So why don't you talk about what's on the screen right now? And they're missing our pretty faces for a few minutes. Back to it. Go ahead.
Yeah. Looking up to get ready for this chart, to explain it a bit better, I was looking at different energy costs throughout North America, and just to give you a quick couple numbers here, was in California from last September to this September, their price per kilowatt hour went from 20 cents to 24 cents, which I found amazing that it was that high.
Yeah, right.
So and then I looked up Virginia, where you are, and it said it was between 8 and 9 cents a kilowatt hour, which is pretty similar to what we have up our way.
Yeah, I think California is more expensive for everything.
For everything, yeah. That's we won't get into why. Yeah.
No, we don't want to go down that road.
But so just thinking that through, right? So if you have a 100 horsepower motor, which is a pretty common one for a fan, it's if you're running 24/7, 365 days a year, because you're running a burner. Right. That, depending on where you live, that costs between $40,000 and $160,000 a year.
Right.
Costs. Yeah. And so, like that's a big difference from the end user standpoint.
Every
And the person that's gonna, get that order is probably often the lowest cost guy. So every $1,000 off their proposal makes a difference to them.
Yeah.
And so so just now back to this chart here. So there's kind of 3 different cases we looked at. This was a real world example that we quoted recently. They were in Canadian dollars, but it's really about the same, regardless. So
and the really what we're talking about is the difference between them anyway, even so.
Exactly right.
And I was surprised to see how much of a difference it was in the end. So
yeah, absolutely. Yeah. So we had 40 the size for the people looking is 4900, which is a 49-inch kind of diameter wheel running at a 1300 RPM. This one is actually it's less efficient. The case that I picked, the first one, so it's a FEI of 0.94. We actually need a bigger than 100 horsepower motor, 125. But the price.
Tell me why you need a bigger motor for something that's smaller than some of the other ones we're going to talk about.
Right. So it's because it's less efficient. It actually takes quite a bit more power to run it.
Okay.
So now you instead of picking a 100 horsepower motor, you're picking the next size up, which is 125. So
Right.
I'm not even counting the costs of that extra wiring, and the things go up with that as well. But the price of just the fan and the motor, let's call it $43,000. And so, but then if you're running that 100 horsepower, and I took some really conservative approaches here. I said,
Yeah,
just use electrical cost of 10 cents a kilowatt hour, and let's run it at like half the time, because I think it's probably not safe to, it's probably not running all 24/7.
Yeah, right.
So then 10 years, and assuming that electrical price doesn't go up, which I think is not the case, that's going to be over 10 years, $355,000 of electricity. And so the 10-year total cost is, just shy of $400,000. And so, relatively speaking, the 10-year cost, the fan is like 10% of that.
Right.
And so now cases 2 and 3 here, you can go up, it's going up one size and two sizes, and then slowing it down to keep the same. It was 25,000 cubic feet an hour and 15.5 inches of static pressure was the case that we picked here. And so now the price of the fan goes up from, say, 43,000 to 47,000. The electrical cost goes from 35 to 30,
right,
which is $5,500 a year. And then so now the total 10-year cost of electricity goes from 355 to 300. So savings of 55,000 over 10 years. And you can kind of see that the 10-year total cost follows that down. And so think of this, Scott, right? You go into your bank and you go to your investment banker goes, hey, do I have a great investment for you? I have, you give me another $10,000 and I'll give it to you back at the end of this year. And I'll keep giving you $10,000 for like the next 10 years.
Right. Yeah.
You'd laugh in his face. You're like, that's too good to be true, right?
It is too good to be true. Yeah.
But
I think
we are.
But this really gets to the idea behind that there's a lot more to an expense of a large industrial product than just the price up front. And you have to be smart about what you're buying up front that also, comes in the back end. We talk about this with our burners. We talk about this with our control systems, that you can upgrade a burner and it can pay itself back. Right. And so, and you're getting more efficiency at that time. And then, unless you really dive into it, you really don't think about it this way. So why don't we talk about case 3 and just kind of wrap it up?
Yeah. And then so you can go one step further and go another one still. And so now just compare it to 43,000 to 53,000, you're going to spend another $10,000 on the upfront cost. But your electrical cost for the end user goes from 35 to 27. So now that's 8,000 a year. And then, so the 10-year total cost goes from, 400,000 now down to 323.
Yeah.
And so, that would be, if it was your own company, it'd be a no-brainer. But the problem is that it's going through a bunch of channels. Right. And if the end user isn't kind of asking those questions, hey, how much am I going to actually pay for this over my life?
Well, and the whole idea of capital expenditures and a budget for capital expenditures versus, dollars that are maintenance dollars. And so a lot of the stuff plays into this, but it's still, you're showing them data. And I would assume that in many of these situations, you show them this data and they may buy the case 2 one, but they're still not going to buy the case 3 one because it's still too much more, even though in the end they know they're not going to get the savings.
Right. Yeah.
Yeah. So is there a point though where there is diminishing returns? I know we only went out to case 3, but if you keep going fan sizes up, is there a point where it probably is an overkill?
Yeah, I mean, probably like 3 sizes bigger than the default one is probably getting kind of, and because everything gets a little bit bigger too, right?
Right.
And
and I guess that is the point. The point that we probably want to mention here is that the fan still has to fit into the boiler design, and so there is probably some flexibility there, like the Goldilocks thing that you were talking about. But if it does get too large, it would impact efficiencies of other things, and it would impact the design and layout of some things.
Yeah,
So,
and like building space takes money too. So
yeah. All right. So before we wrap up, though, there have been some changes in fan regulations, both I think in California, as well as there's been some discussions at the Department of Energy on the federal level. Can you just give us a little bit of a snapshot as to what's going on there and how that might impact current boilers and fans that are out in the field, as well as some new stuff?
Yeah, absolutely. So California has recently, under their Title 20 regulation, mandated that all fan manufacturers supplying fans into California have an FEI greater than 1.0.
Okay.
So for all the burner guys out there that are listening, if you're buying a fan from somebody, ask for that FEI and let them know that it's going to California.
Okay.
There's just a bit of a registration process that the manufacturer has to do.
Mm-hmm.
And then, so kind of building on that, just kind of imminently, the Department of Energy is expected to release some draft legislation on, I think if I could guess, what they were doing is kind of taking the Californian one and looking at it, taking what they like and changing what they don't like. So quite possibly they're just kind of arguing over what FEI number is a reasonable number across the whole continental United States. So yeah, that's kind of where the regulation's at right now.
And is that for and so if you already have a fan, it's not going to affect you. It's going to affect
correct.
Any
it's
new
just new stuff. Yeah. And then
okay.
I think I was reading on the kind of their fact sheet there. California was expecting to save, I want to say it was like $5 billion of electricity over the kind of lifetime of the program.
Yeah. And so environmentally, it makes sense.
Mm-hmm.
And it could make sense from a functional aspect, but it's still an expense that an end user has to take on if they're buying a new fan. And obviously that is not something that is what somebody wants to do.
Yeah, no one wants to spend money, right? Yeah,
right.
Yeah, because you don't have it. Yeah,
exactly. Well, this was a quick half hour. I really enjoyed talking to you. I think it was great for somebody to understand, a portion of their boiler room that's probably not as known to them. They might not be interacting with the fan as often as the burner or the control system, but still a really important piece of the boiler system. So where should somebody go to find you and Northern Blower if they're interested in learning more about the Northern Blowers fans, as well as getting in touch with you if they had any more questions?
Yeah, LinkedIn would be the best spot. We have a very active LinkedIn profile. You can find me there as well, and I'd be happy to connect with anybody and answer any questions.
And what's the website for Northern Blower?
Oh, yeah, northernblower.com. Yeah, very, very hard to remember. Yeah.
All right. Well, that's pretty easy, but some people have dashes, some people,
Oh, yeah.
And well, thank you so much for sharing your insights on boiler fan technology. For those that are watching, stay tuned for more episodes of Inside the Boiler Room. We're doing these monthly. Follow us on YouTube, like us on your audio podcast platform so you don't miss any future episodes. Visit abma.com for more insights on the boiler industry. Sign up for our weekly newsletter there. We're also we're launching a lot of information on the Boiler Expo for 2026. And we'll have some exciting things there. You can also connect with us on social media and LinkedIn. So with that, thank you so much again, Tristen, and we'll see you next month.
Thanks for having me.
All right. Talk to you soon.
Take care.